Hello and welcome dear learners to the NPTEL course on Nutritional Epidemiology, a way towards a healthy life. In the Module 2, Study Designs and Epidemiologic Methods for the Chapter 17, we will be taking the causality in the study design. So, in this chapter, we will be understanding the causality in epidemiology, the concepts of cause in epidemiology, the Rothman's sufficient component causal model, the counterfactual framework, the Hill's criteria for causality, the role of study design in establishing causality, the bias and its impact on causal interface. We will be also studying the measurement error and causality, time-related issues in causality and causal interference in the nutrition epidemiology, followed by case studies. So, what is causality in epidemiology? Let me make you clear that in nutritional epidemiology, exposures are complex and the exposures might be diet patterns, nutrients, behaviors and all this. And there comes a key challenge discussing association versus causation. So, when you talk about distinguishing this with the changes and the changes that you have to take ahead, the important is being highlighted to determine if a specific dietary exposure leads to a change in a health outcome. If the relationship is causal, changing the diet will change the disease burden. If it is merely an association due to confounding, changing the diet will have no effect on the disease. So, you can understand this with an example. So, does high sugar intake cause obesity? The answer might be very different. Or the question may be, is it linked to lifestyle or the socioeconomic status or even a physical activity versus inactivity? So, there is a causality behind the reasons or a disease condition. Let me understand more in clear the concept of cause. So, you can see a necessary cause over here, a factor that must be present for disease to occur. You can see the iodine deficiency is necessary for endemic goiter. So, you may understand that there is a goiter and there is a reason that is called as a cause, that is iodine for causing this. On the other hand, a sufficient cause, a set of factors that inevitably produces the disease. For example, a poor diet, smoking, disease and genetics can also be one among the reasons for this. Probabilistic causation, high obesity versus diabetes. There is a probability that you may get an increased risk. The increased risk can be the risk that can be coming as an outcome, or sometimes it may be uncertainty. There might not be also an association. So, there is a probabilistic causation. The third causation may be deterministic causation. Like you can say cyanide exposure, you may lead to death, or taking high salt, you may have hypertension. There is a deterministic cause, same exposure and same outcome. Rare in NCDs actually, you may not see in NCD. Most nutritional factors are probabilistic in nature. So, you may understand this is very important to understand as a cause for nutritional epidemiology. There might be components, causes and sole determinants. It can be veggies, it can be fruits, it can be diet, it can be milk, it can be salt, it can be even micro or macronutrient deficiency or even excess. So, probabilistic causes is something which is very important to be understand as a concept in epidemiology. Then comes the Rothman's sufficient component cause model. So, what is this? The most diseases are caused by constellation of component causes. So, a sufficient cause, a complete pie. I can give you with the example that a disease occurs when all the component causes come together. You may come out like for example for hypertension, high sodium, low physical activity, smoking, obesity, stress and genetics. So, if you take all this in a cluster, you may come across there is a sufficient reason to state that the disease can be caused away. Okay. So, this is a pie where you can even remove one among, but yes, a cluster of whole can give you one reason actually to bring the disease. The component cause, the blue ones which are highlighted, an individual factor that is genetic, high sodium and low physical activity. where versus a sufficient cause to add up it up actually to make it a complete pie, the minimum set of conditions that produce the disease. What can be the preventing for this? Preventing a disease does not require removing all component cause. So component cause may not be a reason actually that you have to remove it. Breaking just one slice of a sufficient cause. What is sufficient cause being seen? A minimum set of conditions that produce the disease. Okay, so one slice prevent from occurring throughout the specific process. So if you talk about one slice actually to be removed, the stress part, if it is being removed actually, it is sufficient actually to break this cycle. Or even obesity, actually you start reducing it, you can even break this. So preventing is something which is very important actually to be seen as something breaking one slice. So breaking this one slice can be seen as something as a Rothman sufficient component cause model actually, which you can say. Breaking any one of the slice, we will try to understand to preventing the disease pathway. Suppose for example, we are taking the genetics as a slice from this pie to be taken. So disease did not occur through this pathway. The disease will not go through this pathway if you remove the genetic path. Okay. Then comes removing the pie from the pie the high sodium. So disease does not occur through this pathway. So you may say that if you try to remove from high and you are concentrating towards low sodium, you may come across a benefit of this. Removing low physical activity versus you have to improve the activity part. So this can be also something which can be a very path breaking. Also removing smoking, removing obesity and removing stress. So multiple different combinations of component causes can form many different sufficient causes pie, and all leading to a same disease condition and leading to further complex actually the disease condition, which are very important to be taken into this complete pie. Okay, so after understanding this Rothman's part, we can understand the counterfactual framework. So what is a counterfactual framework? There are two figures actually which are being stated for a person who is comparing into a potential outcome, same individual at same time. One is y1 and y0, where you can say hypothetically we can say outcome if exposed and outcome if not exposed. Okay, if exposed actually with fast food, beverages, high sugar and whole lot of things, high blood pressure, increased risk of disease and a poor health, low fruit intake, low veggies, low activities. Okay, where versus in the y1 case, improved health is being seen and the outcome is being seen as a low blood pressure, reduced risk of disease, high fruit intake, high vegetables, improved health. So you can understand from the exposure versus no exposure. Okay, the same individual at the same time. Comparing individual cause effect y1 minus y0. So improve health minus poor health. What is the cause effect? Outcome if exposed y1, outcome if not exposed y0. So the cause effect is the difference between potential outcomes for the same individual. So potential outcomes should be identified with the same individual with the interventions on the part which can give us the counterfactual framework, which is very important for individual cause effect. So now comes the Hill's criteria for causality. There are some criterions which are being given versus what does it means and what are the key questions and the examples which are stated. We will take it one by one. Strength of association. A strong association is most likely to be causal. What is being shown and how strong it is associated, and high salt intake is strongly associated with high blood pressure. Even the dumbbell which is being shown actually shows that if you have a strong inclination or association towards a gym or taking a physical activity, it can reduce your body fat, you can have a controlled BMI and you don't need to take your blood pressure pills. After the strength of association, we will take the consistency. The association is observed repeatedly in different studies, population settings. This is very important. So if you come across such sort of association in different studies, like if the finding consistent come across studies in different population, different countries, many studies in different countries and population show the same association of high salt intake in is associated with higher blood pressure. Temporality. So what is temporality? The cause must precede the effect, means cause is associated with the effect. So did the exposure occur before the outcome? The high salt intake comes before the development of hypertension. So high salt intake should be first and then followed by hypertension. The cause must precede the effect. Temporality. Essential, very important. Then comes the biological gradient, the dose and response. Higher level of exposure lead to higher risk of disease. Suppose higher level of exposure of carbon in the air will lead higher risk of COPD as a disease condition, or even lead to lung cancer. So is there a dose response relationship? We will see. Higher the salt intake, higher the blood pressure. So there is a response actually which is being seen. Higher the salt intake, higher the response, which is very important to be highlighted over here as a biological gradient. Then comes plausibility. The association makes biological sense. How it is? Is there a credible biological explanation for this? Excess salt intake increase fluid retention and vascular resistance, raising the blood pressure. So which is very important to understand over here, that there is a biological sense for taking this as a relationship. You may understand that when there is a sodium depletion, you may find food retention and a vascular resistance raising the blood pressure. Then comes the coherence. The association is consistent with natural history and biology of the disease. Does it fit with what we know about the disease? And if you understand what is a disease, and if there is being seen as an association, you may say that it fits with the knowledge how a salt affects the cardiovascular system. And as we all know, by studying physiology, pathology, and then towards the medicine, there is this fit knowledge which will give us to understand that there is a strong effect of salt on cardiovascular system. Then comes, you have to experiment it. Evidence from the experimental studies and supports the association which is being seen in previous cases. So do experiments show similar result, which is the quick question over here. So salt reduction trials show that there is a lower blood pressure. So which is very relevant over here. So experiment shows that there is a reason actually that if you lower your salt intake, your hypertension also will be reducing it. Then comes specificity. A cause leads to a specific effect. Does the exposure lead to one specific disease? High salt may raise BP, but it is not linked to CVD other outcomes. So there is a specificity involved over here, where your cardiovascular disease has nothing to do only with salt. There might be even other linkages of that. And finally, what is the analogy? Similar exposures are known to cause similar effects. So there are similar exposure with similar effects is something as a key question. So other dietary factors as high sugar also raise blood pressure. There are even other reasons of high stress may also raise, or as a dietary factors there are many associations which can be seen to blood pressure. So no single criteria is sufficient by itself. The more criteria that are met, the stronger the evidence for causality. So what does Hilton's criteria come out over here? So you have to see more criteria which are coming. There are 9 stated criteria over there. If you come across more criteria, you may have an evidence of causality being seen over here, and which is being explained with examples. So you can relate all these Hilton's criteria for a causality to establish a relationship in nutritional epidemiological studies. Now comes the role of study design in establishing causality. Hierarchy of evidence in epidemiology. It is very important that the strength of evidence for causal inference decreases from top to bottom. So if you see the systematic review and meta-analysis of randomized control trials, which are the strongest evidence, and when you go down towards the bottom of the pyramid, actually you can say there is a weakest evidence. What does systematic evidence and meta-analysis give? They give a combined results of multiple high quality randomized trials to provide the most reliable evidence. Okay, and the randomized control trial, which gives experimental studies where participants are randomly assigned to exposure or intervention to minimize the bias and confounding. The cohort studies will give you observational studies that follow exposure and unexposed group over time to see who develops the outcome. So slowly you can understand actually the base that what are the reliance more and who is proving to be given as an higher evidence. Okay, what are the case control trials? The case control trials can be seen as an observational study that look backward, compare the past exposure in cases versus controls. So cases versus control of an previous case. Cross-sectional studies. These are also observational studies that assess exposure and outcome at the same time. Okay, useful for generating hypothesis. So you can generate a hypothesis on the basis of this. Ecological studies, the studies of group or population rather than individual. Country level data, high risk of ecological fallacy can be seen as one of the examples, which has the weakest evidence. Then lastly, the case reports, expert opinion, which can be seen as a descriptive reports of individual cases or individual experts' opinion or views, which has a very weak evidence for causality. So this way you can understand the hierarchy of evidence in epidemiology, which can be seen as one of the strength of evidence to prove that the causal inference decrease from the top to the bottom, where the top which can see the systematic reviews and meta-analysis. Now we can understand the bias and its impact on causal inference. So there is a selection bias, there is an information bias and a confounding bias. So what is a selection bias? A selection bias is for example a healthy voluntary effect. So target population where 50% are healthy and 50 are less healthy. So in a target population you can see some of the group of the individuals are very healthy active and less healthy active. So the participants systematically differ from the target, and healthy voluntary effect we can see the other actually versus to the other can who are taking the negative exposure of junk food and fast food and all those. So 80% after the study sample are being seen as healthy and 20% less healthy. So volunteer who join or they are enrolled to join actually for this. So correlation with the exposure diet those are being given versus to the outcome of the disease. So there might be some level of selection bias which may come whom we are selecting, whom we are enrolling and how they are volunteering join. So voluntary is being seen as an effect of being stated as a selection bias over here. Then comes information bias. So information bias, that is recall bias. Information bias as a faculty memory in cases where a person who is being stated to have a recall attempt. So diet 5 years ago is very difficult to understand, or recall attempt diet 5 years ago. So miscalcification, so cases with diasis and cases with control that is healthy. So errors might be there in the data collection. So you can say cases search memory harder and perhaps over reporting unhealthy items, which might create some sort of systematic error absent in control. So diet we can say healthy towards a disease. Then comes the confounding bias, where that is a residual confounding. Confounding bias, that is a hidden third factor variable that might be high smoking, alcohol or some sort of culinarity we can say with a high exposure of sugar, candies, beverages. Or sometimes you may find that there is no link actually which may lead to high BMI or obesity. So there is a false associated observation. So residual confounding might be a lingering bias, false bias even after the adjustment. So it looks like a connection but it doesn't develop. So causal inference requires rigorous control of these biases using a robust study design, especially the RCTs. Measurement error and causality. So how to minimize the measurement error? You can use a validated and standardized tool which is advisable over here. Train and monitor the interviewers actually who are being taking, and this is the one of finest way actually to reduce the measurement errors. Use repeated measurements actually, which will reduce and minimally actually it will adjust the state. Calibrate instruments regularly, which is a very important part. Use biomarkers when possible, but this is something a costly affair. And quality controls and data auditing, which is being advised actually to see that there might be an impact of random error and a systematic error. Random error usually biases the effect estimates towards a null or no effect. Okay, and the systematic error can bias the effect estimate towards or away from the null, or even reverse the association. Okay, so this is very important to understand the differences between this. Example, dietary assessment, where in the example of random error, like day to day variation, eat food intake recall. I ate 2 fruits yesterday, I ate 3 foods yesterday, I drank 1 cup of tea, I drank 2 cups of tea, or even a green tea versus a black tea. So this leads to underestimation of the true association between fruit intake and disease, or tea intake and a disease. Where in the systematic error, people with disease may underreport unhealthy foods. I should not tell about my junk food intake if I have to, or I should not talk about such an habit actually which may. So can overestimate or even create a false association. So what is the key takeaway from the measurement error and causality over here? Measurement error is inevitable, you cannot even stop it, but it can be minimized with some sort of an efforts actually. Random error usually weakens the association and you should try to work. Systematic error can lead to misleading conclusion, which is being seen in example of junk food. Accurate measurement strengthens the causal inference, which is very important, and you should try to minimize the measurement error. Time related issues in causality. Time related issue in causality, exploring the chronological order. Temporality as then start the exposure, true causality, and you can see the outcome might be from 1 year, 2 years or 5 years. So temporality for exposure must precede the outcome. Then latency period. So you can say the latency period might be a decade long latency, like if we have an exposure of high diet actually, which is more like a junk food or even a high carbon diet or high beverages, you may see as a latency period that a decade long latency may lead to some level of outcomes on your disease, might be an exposure to tobacco or even maybe seeing a cigarette after years may come up as a delayed effect. Reverse causation, the confusing chronology. Diet changed and the outcome is like low risk. No reverse actually, or a reverse causation where you can say observed diet change and a detectable outcome. So occurs when an undiagnosed disease or symptoms or exposure may be creating. So a statistical link and common in cross-sectional studies. Causal inference in nutritional epidemiology. So causal inference in nutritional epidemiology, key limitations. While establishing causality from diet disease association is challenging, complexity of dietary exposure. So people consume food and not isolated nutrient. So diets are complex mixtures, while interaction, the synergy or antagonism between nutrients and bioactive compounds. For example, it is very difficult to know whether the benefit comes from one nutrient or the whole dietary pattern. Measurement errors already I have stated to you. Miscalcification of exposure usually basis results towards the null or unpredictable directions. Confounding, for as an example, even after adjustment, residual confounding may remain as a distort association. You may say that physical activity, socioeconomic status, smoking, education and even health consciousness. Reverse causation. Example, low sugar intake associated with diabetes may reflect dietary change after diagnosis and not a proactive effect. Long latency period requires a long follow-up or a large as a sample size, which are costly and difficult to manage. So long latency is also being seen as some of a limitation. Time varying exposure. So inadequate capture of dietary changes lead to exposure of, and it can be seen as a very miscalcification. Ethical constraints. If it is unethical or impractical to randomize people to harmful or unhealthy diet, we cannot really assign high saturated fats or trans fats to participants into a trial. So it is ethically constrained which is coming. Limited external validity of trials can be seen, or even small effect sizes which may come as an example, like a true small effect may be missed or exaggerated. Sometimes you may come up with reporting bias, which is a very important. When example as publication bias creates an incomplete or misleading picture of the evidence, and which is sometimes giving a very difference in the opinion. There are a few case studies that I want to highlight over here. The global case study is nutritional causality, exploring the complex pathways. A salt intake and hypertension direct pathway, that is a start exposure 0, and you can understand that it's a direct response, Hill's biological gradient, and you have understood it. The outcome results will be seen as hypertension increasing 160/90 plus in 5 years. You may see a fruit vegetable intake and CVD. High fruits, high veggies, dose response, Hill's biological gradients again coming over here. Mechanism is antioxidant effect, fiber intake, potassium level, and CVD risk reduction, which is very important to see over here. Then comes saturated fats. If we talk about the probabilistic curve actually, which can see that genetics high, lifestyle moving towards a high intakes, mechanical factors affecting. So you may see the reduced CVD if your genetics are lower, and lifestyle and all those factors, probability reducing by 30%. Sufficient caused if you find a component cause acts alongside the genetics and it is even causing the effect. So there is a triangulation which is coming with a global evidence for causation, mechanistic plausibility versus the RCT. And ultra processed foods and obesity, there is a very strong connection. Ultra processed food, latency timelines actually which can say, and weight gains actually which is giving. So moving from observation to causation in nutrition is very important, and no single study proves absolute causation. So causality is inferred through the consistent coherent weights of evidence across all domains. So evidence is also important for this part. Indian case study in causality, exploring diet and environmental pathways. Diabetes 2 in urban India, and you can see the start exposure of the urban lifestyle which is being shifting from food which is being consumed towards over 10 years of outcomes, which we can say type 2 diabetes is increasing actually. This is also Hill's biological gradient. Then is CVD in South India, saturated fats and coconut oil, reduce risk. So coconut oil intake, genetic lifestyle and all that, and the probability is that there is a CVD and it has been seen as a disease risk. Tobacco exposure, again a graduated outcome, head and neck cancer. Then come childhood undernutrition and diarrhea, lack of clean water, lack of hand washing, poor sanitation, causing effect is like a childhood diarrhea which occurs on, and broken single slice prevents the disease from occurring. Either clean water or even proper food, or underlying malnutrition can be reduced by providing a proper sanitation and all those. Air pollution related to respiratory disease in major Indian cities. So shorten latency outcome as an asthma, if you have to reduce detectable asthma symptoms, actually a longer effect, so you can see the detectable lung cancer as an causation. So triangulation, observation plus trials overcomes biases from confounding and reverse causation. So with this we come and enter into the chapter. Causality in study design refers to determining whether an exposure truly leads to an outcome beyond mere association. So there is an association which is also important, and a causation is also very important. It relies on key components such as temporality, control of bias and consideration of confounding factors. You have seen the framework like Austin Bradford's Hill criteria and Kenneth Rothman's cost model, which is a help actually to give you a very guided interpretation. Stronger study designs such as systematic reviews, meta-analysis are something which is being at an higher side for evidence, and RCT provide more reliable evidence, though observation studies are often used in nutrition. However, bias, measurement error and time related issues can distort causal inference. Therefore, causality is the best established, though a combination of multiple studies and critical evaluation. So with this, we come an end to this chapter. Thank you very much. You can use these references for understanding the causal inference in more detail. Thank you.